we left off. So the concept of topology actually has three components. We have the so-called connectivity, okay, rule. Then we have the containment rule, okay. And I said that the containment has to do with polygons. Are you okay? Polygon arc topology. So it deals with the fact that every polygon is made up of arcs. Are you okay? An enclosed set of arcs. And then also that it's only an enclosed polygon that we can measure the area for, as we explained. Polygons are represented as a series of XY coordinates. Is that okay? So if I go back, I don't know if we described it. Okay, for the line we didn't do that, but obviously everything that we represent geographically, we can actually in GIS we are representing it with what? A table. Are you okay? So when you look at this one, we have a list of arcs. Okay, so polygon B is made up of arc 1, 6, 8, and 5. Are you okay? So polygon B is made up of arcs 1, 3, 6, and 5. Okay. Polygon C is made up of arc 2, 9, and 6. Are you okay? And then 4. Are you okay? So we shouldn't forget about this one. Okay, so arc 4, 9, 6, 2. That is also polygon F is made up of 10, 9, 8. Are you okay? Polygon F is a middle one, 8, 9, 10, 0, and 7. Are you okay? We're getting 0 and 7. So where is 0? For F, I don't know where he's getting the 0 from, but obviously every single arc that forms part of the polygon should be counted. Are you okay? All right, so this is how GIS keeps data on polygons. Are you okay? As records, as rows like this. And then the attributes are added so that we have the so-called attribute table. The third component of the concept of topology is the contiguity. So contiguity says that every arc has a direction. Are you okay? So anytime we sleep, we go to bed and the lights go off and wake up, you know, because we've been dreaming, we are in a different world, isn't it? And yeah, when we wake up, we just want to find out where the switch is. Then we start tapping the bed, isn't it? The computer has learned from this. You know, those who design some of the software that's able to keep direction so that you know where the car is moving. For example, on your Uber app, you see that the car is moving this way instead of that way. How does the computer know that you are moving left to right, or whether you are permitted to move left to right or right to left? How does it know? It maintains a list of polygons on the left and the right side of each arc. In other words, when you wake up in the middle of the night, you start touching the bed. And once you know that the fan is on your left, you know that, okay, if the fan is to my left, then on my right, I should have the light switch. You see, it's something we do subconsciously, but it's something that really can be applied. Are you okay? So I'm sure someone has even made a PhD out of something like this. You know, it's a very interesting thing. We take it for granted, but I have experienced it, so I know that definitely is that concept that is being used here. So the polygon to the left or right of an arc tells us the direction that we are moving. So when you look closely at this one, then we can see that this arc 1, the left polygon is actually A, and then the right polygon is B. Okay, so how did I get it right like that? Because it does make sense to look at it that way. How did I get to know that this? How did I get this one right? Okay, I got it right because I look at 1. If you were walking along this arc, when you turn to the left, you'll be seeing A, which is this area, this outside area. When you look to your right, you see this field B, which is polygon B. So the alphabets are actually the polygons and the numbers are the arcs or the lines. Is that okay? All right, so now we have let's take a last example. Let's look at arc 10. Arc 10. So you try it yourself, look at it and see if you can figure out. Don't look at the table. Just look at the don't look at the table. Look on the left hand side, see if you can tell the left polygon and the right polygon for arc number 10. Okay, so a few seconds. If it takes so long, it means you don't understand. All right, so what you should look out for is the arrow. So the arrow here is pointing in this direction. I don't know if you can see. All right, so the arrow is pointing in this direction. So if I'm going this way, on my left, I'll find D. On my right, I'll find F. Okay, I think I have something else here. This is 10. This is 3. Okay, so what we have here is a little different, but it's 10 is down here, huh? So I'm looking at the wrong place. All right. Yes, otherwise it would have been wrong. So 10, the left polygon is D and the right polygon is F. Okay, so that is how we do it. This is how we do it. Okay, so for 10 and then for 1, this is what we have. Okay, so this is how contiguity works. Okay, so a few things that we have learned in topology. The components of topology are 1, connectivity, 2, containment or polygon arc. Then we have contiguity, which is the direction of every arc. Which direction is inherent? Okay, how do we tell that this is the direction that you're moving? All right, so that is that for you. Topology for you, very simple. But normally this is programmed into the computer, and then the computer does that. It does it automatically. All right, the next topic is, if you have any question you can ask. If you don't have a question, let's move to the next topic. If you just join, don't ask a question. If you just join, don't ask a question. So basically, map overlay is the next topic. Okay, if you don't have yes.
Good afternoon.
You just join me and you want to ask a question.
I want to plead with you.
Do you want to ask a question on the topic that you just joined in?
Yes, sir.
So how are you gonna? You don't do that. You don't do that. Your question will sound funny. That is the whole thing. So you don't normally allow to ask a question if you are not there. So you have to listen first, then you have the right to ask a question because you are not there. So how are you going to ask a question?
I get you. It's just something that I wanted you to clarify. That's it.
Go ahead.
Okay. Back to the page that you just moved. Okay. You did the 10, which I quickly got that one. But the one that you did, the earlier one that you did, I was trying to get something, but that is what I want you to clarify. But the 10, I got it because you said it's going in the arrow. It's going in that arrow. So what you see on your right is the F, and what you see on your left is the D.
Okay. So the one that you are seeing here,
okay,
one is this one. Yeah. In other words, it's referring to this line here. So it's referring to this arc. This arc starts from, I'm just doing my best to show you, to use this. So the arc 1 starts from here and then ends here. I hope you understand this. Do you understand what I've just done?
You said arc 1 starts from this side to this side.
You see where the star is? The star is the node, the beginning and then the end of the arc number
Okay.
one. Of arc number one. You understand that?
Yes, sir.
Okay. So arc number one starts from here, the star, where the star is, and then moves through where I've put the love sign. Okay, and then comes back down here.
Okay.
So first you have to identify the arc. Then when you have identified the arc, then you can now look for what is on the left or the right.
Okay.
Once the next thing you have to do is to then find the direction that you want to store. You want the computer to store for that arc. Okay, so the direction that we can see visibly with our eyes is actually going in the direction of the arrow. So it's going this way. Can you see that black arrow down here?
I can see that arrowhead. Yeah.
Yeah, exactly. It ends right here, isn't it? Okay, great.
Yes, sir.
So that means that if this were a network, if it were water flowing through it, then the water will be flowing in this direction up here, and then go. So it will force the water. We can only move in this direction.
Okay.
Okay. All right. Great. How does a computer know it? That's the direction. It's not trivial. So the example I gave you is when you go to bed and you wake up and you've had a very bad dream. So in the dream you were a fisherman. In the dream you were giving speech as a president of the US and all these things have happened. Are you okay? So you wake up,
Yes, sir.
you have been to another world. You just wake up and you are confused and the lights are off because of ECG. So you've lost your bearing on the bed. I don't know if anybody, I'm the only person who has experienced this before. We experience it all the time. You wake up.
Yeah, it does.
It happens
It
a
does
lot when
happen.
you're a child. I think when you're a child, you experience that a lot. And so you need to now figure out what is actually, where am I facing? Because you see, when you sleep and you move a lot, some of you, when you sleep at one place. Some of us, when we sleep, we can move all over the place. Are you okay? So now you don't even know, you've lost your bearing on the bed. So the question now is, where is the switch? Because when you are terrified, because you had a horrible dream. So how do you know that the switch is to your left or right? Because remember that you have actually you are tossed and turned on the bed. To know whether you are the switch is to your left or your right, you actually need to sometimes use your leg to hit the bed and check if the pillow is here or there, and do a whole lot of things. If what you are trying to do, you are trying to find out what is to your left and what is to your right. Or let me just say, what is at your feet or what is at your head. Then you get to know what is also on the other side. In other words, you are orienting yourself. Are you okay? So the same thing is happening here.
Very
So
well.
when you got a 10 right, yes. But the reason I'm telling the story again is that if you look at the one, the interesting thing is that there's a polygon that is difficult to actually identify. And that polygon is actually within this area. All these areas is polygon A. All these areas. Anywhere outside this whole thing is A. Do you get that? Do you get that assumption?
Anywhere outside this area is
anywhere around this. So the A that we've written here is actually all these areas are A.
Okay.
Are you okay?
Yes, sir.
And that is why our left polygon is A. And then our right polygon is B. Because remember that to our left, if you are walking along this line, to our left, you can't visibly see any particular polygon there, right? Can you? You can't.
Yeah.
Yes, exactly. But that is the polygon A that you are seeing. The A you are seeing there is like anywhere outside, as if we are living in an island. Are you okay? So that is why you probably wouldn't get the arc 1 correct. But when you do arc 2, for example, well, what would you get? I don't know if you can try that one. What is arc 2? Do the actual, let me see. Well, what will be to your left? What will be to your right?
At 2, I think my right will be C.
Okay, and then your left to be?
Your left is what I can't find.
Your left is what I told you, that any other area outside of these polygons, B, C, D, E, F, is A.
Okay,
so A is like the world. It's like the world. Are you okay?
Yeah.
The world. Anything outside.
Or the sea, and then this one is the island. Okay.
Okay. Anyway, for information, I hardly ask questions about this, what we are doing right now, even though it's important to know. Okay, but it's good to know.
Yeah.
Yes. Yeah, but you never know. These days, the questions that we ask you, they are very analytical. So yes, it's good to understand what we are doing. Okay. All right. Let's talk about map overlay.
Right.
You're welcome. So this is Nanaya, right? Is it Nanaya? Is that Nanaya? Who was speaking? Who was I speaking to?
Taufik.
Taufik, okay.
Taufik, yeah.
I see your name, but I think I've heard Taufik. I've heard the name before, but I've never seen the spelling. All right.
Okay. No, I'm just using this one. This is not the correct spelling, actually.
Oh, really? Then I've got it. I'm gonna give me the right. I'm taking attendance. What's spell it?
T-A-W.
Yes.
F-I-K.
F-I-K. Okay. Taufik. All right. It's a very nice name. What is it? An English name or what? What's the?
It's an Arabic name.
Okay. Very nice name. All right. Let's move on. Let's talk about map overlay. I think we know what overlays are. Is that okay? Overlays are a way of separating the data. Are you okay? So we can give. So you can't talk about overlay without talking about themes. Let me just write a word down. You can't talk about overlay without talking about themes. Okay, or a theme. Okay, so what is a theme? The theme is like a topic or okay, a certain subjects. So we normally collect data by separating the data into several layers. Okay, this is done in AutoCAD, but GIS also has a way of keeping its own layers. Okay, so this concept is common between CAD systems and then GIS. Okay, now for the same geographic region, we have several layers. Are you okay? All right, for the same geographic region, we have several. So at a particular latitude and longitude, at a particular location, you can have different layers. So the diagram you are seeing here is a typical example. For example, the top layer is some kind of black and white imagery of the area. The next one is another layer, that could be something else, soil type or something. The third one could be something on vegetation. Are you okay? And the last one could be just some kind of 1950 map, which we have georeferenced. So we can put all these together and stick them together. And then when we do that, then we have map overlay. When you do it well, you can turn off layers, turn layers back on. Okay, so the concept of just having different data themes or different data layers, it's a very good one. Okay, so that we can actually do analysis. For example, when we have a points layer of borehole locations, we want to keep it as one layer. Is that okay? But when we have point data on electric poles, we don't want to put it on the same layer. We want to, because they are two different themes or topics. Okay, one is on light poles, okay, and the other one is on what do you call it, boreholes. Is that okay? Borehole locations. So we separate data into different layers and we can recombine them. The whole idea of separating data into different layers, data layers, is to recombine those layers. Is that okay? All right. So map layers allow us to combine several spatial data sets, i.e. points, lines, or polygons, so that we can create a new output vector data set. Is that okay? All right. Now remember that once we talk about points, lines, and polygons, this is called vector. So put it in your mind. Later we'll talk more about vector model. But then once you hear of points, lines, and polygons, we are referring to what the so-called vector model. Is that okay? The same way in topology, we were dealing with polygons and lines. So that one is also vector. So take note of that. I just want to draw your attention to something that I will talk about later on. All right. So we can combine the layers by just doing what we used to do in set theory. If you remember the set theory that we learned in GHS or whatever, wherever we learned it, O level or whatever it was. Union overlay. You remember we did union, we had intersection, then we had symmetric difference. Is that okay? All right. So if I do this, A union B, A union B, then in map overlay, it's like taking one layer for the same region and then simply add them together. So if I have some kind of straight here and I have something circular here, then I can combine them, add them up and get a new layer, which now has, okay, so equal to a new layer with the line and then with that circular thing, that feature. So this feature could be this could be a lake and this could be a road. So now I have done a union overlay. Are you okay? This is how it looks like. I never write this in the notes. It will never be written, but this is what is actually happening. It's like what we used to do in maths when we do, you know, this thing, A union B. Yeah. Okay. Now A intersection B will be here. Is that okay? And so that can also be described. Are you okay? In terms of maybe trying to find out which constituencies will be affected if a certain gas pipeline project is undertaken. Then you have to overlay and then find a common area. That is also the so-called intersect overlay. So in the intersect overlay, we find the inputs, okay, the overlap, we look for the inputs, the overlap between the inputs, and then we retain it. But then in the symmetric difference, rather reject it. Are you okay? Anything else? It's okay apart from the intersected area. So intersect overlay is almost the opposite of symmetric difference. So intersect will be like A intersection B. Okay, so intersect will be like A intersection B. Don't write this in exam. I'm using it to help you to understand. What if you never understood this? In that case, then you have a problem, isn't it? Okay. Using the whiteboard here is always funny. I'm trying to just move to the next page. But okay, I think I get a new page now. And then how do I write? Oh, man. It's not the best. I wish I were using my own, you know, Microsoft whiteboard. But even the Microsoft whiteboard isn't working. Okay, I think it's working now. Let me quickly go and share that one. Microsoft whiteboard. Where are you? There you go. Okay, so with this one, excuse me. I need to clean up. Okay. So, oh, look at me. Okay, let's see if I have it clean up. It's such a shame. This thing was just working right now. Okay, guys, let's move on. Let's move on. I would have loved to do an illustration, but it's not working. Let me just let me show you. I have a diagram here. This one will explain it. Okay, so here I'm combining this layer and this layer and that layer, and I'm getting that layer. Are you okay? All right. So that's union in what do you call it? Union overlay. It's okay. Union overlay, not union intersect. Then we have intersect overlay. I take this layer, take that layer, I find the intersection, and then the intersection becomes the new layer. So at the end of an overlay operation, we obtain a new what? Vector output layer. Is that okay? So here the blue, the cyan area That is the area that will be affected. It's assumed that we are having a pipeline project, some kind of pipeline project. Okay, and then we need to find out, okay, which areas will be affected. Are you okay? These concessions, okay. Said okay, this part of it will be affected, or what's the size of area of concessions that will be affected? Are you okay? By the so-called projects. Are you okay? And that can have that. So the symmetric difference is actually finding the intersection between two layers. Okay, so assume we have one layer, another layer like that. It's not easy drawing with this one, but I'll try. So we have this area on the first layer. Then we have this on the second layer. So when I overlay the first layer A, second layer, then the results should be, the intersection area will look like the rectangle. Is that okay? But that's what we don't want. So you end up having something like, you know, a hollow polygon. Are you okay? So you have a combination of these two with the triangle, but then this area is actually hollow. There's nothing in here. That is the symmetric difference overlay. Okay, so symmetric difference overlay. At the end of the day, you have something like an island for this one. Okay, I think basically that's that. We are moving on to the next one. Unless you have a question, if you have a question, please put up your hand. Let me hear from you. Otherwise, I'm changing topics. I assume you understand what I'm talking about. Are we good with the whole idea of overlays, map overlays? Are we okay? All right, let's move on. One of the things that we can do with overlay is data extraction. We can more or less click. Are you okay? So as you can see, we have a large data set. We want to cut part of it. So if you have, say, all the road layers in Ghana, you can actually cut it with the Greater Accra regional boundary. Okay, so that kind of becomes extracting data. You're extracting data. Is that okay? It's like a cookie cutter. Is that okay? We can cut some part of data, or clip part of the data, or mask part of the data using the concept of what layers. Is that okay? Without the concept of layers, everything will be bundled together in one layer, and it's not going to help anybody. And we all know that in AutoCAD, you can actually create one big layer of everything, but separating it helps a lot. You know, separating it into different layers helps a lot. All right. So data extraction is like one of the advantages of uses of data overlay, map overlay. Is that okay? Map overlay. All right. So here we're talking about map algebra and raster analysis because you see all the things that we've been talking about is vector. Later, like I said, we talk about vector and raster. We will get to know that in GIS, two things that are very important is the raster and the vector model. Raster and the vector model. So you have to be careful you don't write raster like this or raster like that with an O and R. Okay, so it's not this. It's spelled like that. Raster is spelled like this. So vector is points, lines, and polygons. Whilst raster is more of a picture. Okay, pixels. All right, so the way we process or handle GIS, sometimes we seem to be working more in the vector or the raster mode. Is that okay? So map algebra and raster analysis, you know, that is when we are actually combining different raster layers. That is what happens then. And then every other thing that we do in overlay analysis is going to be vector. Is that okay? All right. So let's move on and let's talk about the next topic. If you have any question in map overlay and themes, I will be talking about the next topic. Do you have any question or you get it? Do you get the practical, the application of overlay. Yeah. Do you get an application of overlay? I can do an analysis on all boreholes together in GIS because I've separated it as a layer, as a single layer. Okay. So the idea of creating layers and using layers is not only for data extraction, but to allow me to easily handle different topics differently. Are you okay? Different themes, data themes differently. All right, so there we go. Let's talk about buffer operations. Buffer operations are used, or buffering is used to constrain the space around individual features. Okay, we have 10 minutes. When the 10 minutes elapse, I want you to pick the same link. Okay, we have 10 minutes. When the 10 minutes elapse, let's pick the same link, and then we'll do a little bit, then we close. I don't want to talk plenty. I think sometimes I talk too much. Okay, so what is buffering? What is buffering? Buffering is constraining the space around individual land features, or whatever you want, coverage features. Are you okay? But features, we're talking about things around us, buildings, trees, any object. Look around you. Okay, if you're actually near to a window, look out. All the things you are seeing nowadays, they belong to, they are called features, like I said. All right. So how do you constrain the space around individual land features? Is that okay? How do we do that? Okay, example is when you want to, do a farm belt. The farmers have what they call the farm belt. Is that okay? So if you have a farm that's looking more like this, you can do a buffer around it like that. What it means is that you are going to be creating some space here, okay, around the farm, so that when fire, comes around, when there's fire outbreak, you are not going to be affected. The fire will be just going around your farm, okay, but it will never enter your farm, simply because you've created a buffer. And what is that? It means that you are constraining space around an object. What is the object? The actual object is your farm, okay? The object of interest is your farm. So now, that is the simple application of what? A buffer zone, or a buffer, or buffering. Exactly. Constrain a space. You can do it for a point as well. You can decide that I have a point. I've arrested someone here, house arrest. I don't want him to move 2 kilometers away from this house. All right. So what I do is that I make a buffer around where the person is. I couldn't do it very well. So it's like the point is not at the center. Okay. But that's the idea of a buffer, that it should allow us to constrain the space around the particular object of interest. Is that okay? All right. So now this is called a point buffer. And then this one is called the polygonal buffer. Then you can have a line buffer. So if you have a line going like that, you can constrain the space around the line by drawing parallel lines like that. Then you can now cap it with a semicircle like that. Sorry, I'm not drawing very well. Please take note of that. I'm trying to draw something perfect, but I'm using the mouse. I'm not using a chalk or anything like that. So bear with me. So we can just cap it this way, or we can cap it, okay, with a rectangular end like that. So the parallel lines go. Okay. So the area, the buffer region is always a polygon. Is that okay? So this is the buffer region. Okay, this is the buffer region. For the farm, the buffer area, this is an outer buffer. Is that okay? So with polygonal buffer, you can have an inner or an outer buffer. So this is an outer buffer because the farm is inside. Is that okay? If we were to do, but why would you even do an outer buffer for a farm belt and not an inner buffer? So the inner buffer is where you take the object and then you, instead of you to buffer outside it, you buffer within it. So the buffer goes inside the object. Okay. So this is the buffer area, the buffer zone or buffer area. Okay, an engineer should know something about buffering. Is that okay? Okay, so now for the circular polygon that is generated as a result of the point buffer. So we have this area. So we have point buffer, and we have polygonal buffer or polygon buffer. Then we have line buffer. Okay, so you can have a point buffer, a line buffer, and then a polygon buffer. Is that okay? And they all have their own applications. So the circular point buffer, the result of this point buffer is a circular polygon. The result of an outer or inner buffer is some kind of hollow kind of polygon. Are you okay? A polygon with a hole inside it. Is that okay? Then we have a normal polygon as the output of a linear buffer. Is that okay? All right. Now, the application of the point buffer is that we can use it to find out where wireless signals are reaching. Are you okay? We can use that to determine where are the wireless signals reaching. All right. Then for the farm, I think I've talked about that. The linear buffer, if you have a road and you want to quickly know, okay, which buildings need to be pulled off, you can always set a buffer to the left and to the, on each side of the road, the center line, and then you pull down buildings. That's how people pull down. I hope that's how people pull down. I hope it's okay. I hope. Because sometimes you pull down a building and realize that the road didn't pass there. Are you okay? So that is application. You can think outside the box. Given any scenario, you can almost tell if you can apply, some kind of buffer to it and use it to solve a problem. Is that okay? All right. So let me just take this off for a moment. All right. So down here, you can see that that's point buffer. We have a point buffer here. We have a linear buffer here. Then here we have a polygon buffer. And the final output of the buffering is always some kind of polygon. Is that okay? You always have a polygon at the end. You can also buffer pixels, as in the raster model. Is that okay? We can buffer pixels. So pixels are like squares. Okay, that make up a picture. Is that okay? The squares that make up a picture. Later we'll talk more about that. So we can have the circular polygon as the output. You always specify a buffer distance. I think I didn't talk about that. So the distance between the center and then the actual peripheries of the circular polygon, the circumference of the of the circular polygon. So circular polygon, another name for is a circle. Is that okay? But just like in GIS, we don't have something like circle. We have polygon, lines and polygon, points, lines and polygons. So this distance here is the buffer distance. The distance specified here. It can be 50 meters. Okay, it could be 20 meters. It depends on the application. All right, so you need to think outside the box and know what we are actually looking for. So for the linear or line buffer or line segments, we can always do parallel lines at a certain distance, m, which is the buffer distance. Okay, so here the buffer distance is actually from here to here. So it's almost a constant value if you are really doing it. Or you can also set it to an attribute inside the software. Within the software, you can say that, well, I'm setting certain distances. Use that for the buffering. Okay, because every single line will be represented as a record. Okay. All right. So we are ending this section on the topic buffering. Let me show you the polygon quickly. before the whole thing cuts. Let me show you. So this is the line linear buffer. Like I said, polygonal buffer, we have two options, inner and what? Outer buffer. So take note of that. Inner and outer buffer. Sometimes you put negative and it will do the inner or outer buffer. And remember, we'll be doing practicals. All these things I'm talking about, we'll pick some and we do practical on them. So try to understand how it works. Is that okay? All right, so we will continue when this session ends with the same link. Please don't take long to join so that we will not waste too much time. Okay. All right. Meanwhile, if you have a question, get it ready.